Nobel laureate Professor Eric Cornell and Professor Ana Maria Rey. And they will be with us this week with various activities that we have been telling you about. So please join us in this wonderful celebration. And today we will start with Professor Jun Ye. So if we can, you see, very professional. No, we have to change the cable here. Yeah, experimental.
Yeah.
Hey, that's how it works.
We're at your service if you need help.
Electrons got to go the right way.
Oh, let me.
So Professor Jen, thank you very much for coming. So he works at GILA, that together with NIST, that is the National Institute of Standards and Technology in US, they have this big research group. They can then tell you more about it when you talk with them. And so Professor Jen is going to be talking to us about this wonderful experimental work that he does, creating the more precise clocks that we have now on Earth. Professor Jun Ye, he did his PhD, so let's see if I get it correct. Actually, we were discussing now at lunch, I didn't know, there is a web page that you can go and it's called academictree.org. So you can follow like the genealogical academic tree of people. So Professor Jun Ye, he did his undergraduate studies in China, and then he moved to US. He did his master's degree with Professor Marlon Scully, that maybe the people knows works in quantum optics, knows there is a textbook written by this professor. And if we go a little bit in this tree, Professor Marlon Scully was a student of Lamb, that was a student of Oppenheimer, that was a student of Max Born. So you see this heritage. And also this was from his master's degree, because if we go to his PhD degree, he did his PhD under the supervision of John Hall at GILA, that is also a Nobel laureate for the frequency comb. So, and then Professor Jun Ye has been following this heritage and is going to be telling us about his wonderful experimental work. Again, thank you very much, and we are very happy to listen to you. Please.
Thank you. Thank you, Alejandra. Very nice. Well, certainly it's been an incredible pleasure to come here and feel very honored. Thank you for inviting us. And I do feel very strongly connected, even though it's only been my second trip. But one of my best friends, Ana Maria Rey, we have been working together for 17 years. Time flies, 2008. And we were just over lunch, even with Alejandra. We have common friends. Your PhD thesis advisor turned out to be a quantum optician who I have known for 25 years. So it's a really small world. And it's a privilege to come to tell you a little bit about clocks, fundamental physics, and hopefully in the next 45, 50 minutes, you'll get to enjoy a little bit of a joke and the physics and combined together. So let's get going. Maybe I'll start with a slide of fundamental physics. If you look at it, it's maybe a more sort of street person's view of fundamental physics. It's not condensed matter physics, it's not high energy physics, but really from the perspective of experimentalist, we build microscopes to understand standard models, to understand mysteries, why neutrino has mass, where's quantum gravity, do we ever will be able to probe this on Earth instead of having to really rely on the black holes and so on. Another tool we build is telescope by looking out to astrophysics where a lot of mysteries still linger. But also you have heard some of the very successful recent story of gravitational waves and so on, detecting, opening up new windows of looking into astrophysics. On the third pillar, I would argue, for fundamental physics is really quantum complexity today. That's because quantum physics describes many-body entanglement, describes phases of condensed matter, describes very vibrant field of quantum information processing, whether it's gathering information, processing information, and so on, or transmitting information. And all of this plays a role of defining the frontiers of a measurement science. And you can see, because of that, the connection between this pillar and the other two pillars, microscope and telescope, is nothing but building on the frontiers of a precision measurement. And you're going to hear a lot this week. Professor Eric Cornell is going to tell you some of the very best microscopes to hope to go even beyond the standard model to discover physics that we do not understand. We know the current standard model is not complete. And he's going to tell you how he's going to look further, peel the nature up another layer to see what secrets are lying behind, right? Why our current physics model is not complete. Telescope, perhaps by building clocks and so on, will help us to detect dark matters, gravitational waves. And Professor James Thompson and Maria Ray is going to tell you a lot about quantum complexity. And altogether, James is also going to tell you about matter wave interferometry and so on. And clearly, this is what we do the best in the sense of Agila, where we have this combination of NIST fellows and the University of Colorado faculty members working together to, in some sense, across the entire area of physics, but emphasizing on the tool building, where relying on quantum complexity and turn this into a tool to open new chapters for fundamental physics. And I hope some of you later will come to Colorado and do this kind of physics. It's very fun. And it actually, now I forgot one thing. Before I left for Columbia, Anna Maria said, every physics lecture in Columbia has to start with a dance. So I thought I'm going to wear this and start to dance around. Is that true or not? That's not, that maybe she was picking on me, you know. It's actually totally. But actually, I'm wearing this, telling you actually a different story, okay? I made that up a little bit. Anna Maria wouldn't do that to me. You know, to do this kind of physics requires a lot of teamwork. I have no expertise in high energy physics. Well, I know how to build lasers better. I know how to put atoms together and do physics with it. So in some sense, by having people who have expertise in high energy physics, in theory, in condensed matter physics, in quantum information, teaches us how to build better sensors, how to use entanglement for measurements in the future, and so on. This is where defining sort of the physics frontiers. Coming with different experts, you are really, really deep into certain area, but you have other experts that's going to collaborate with you. So the very reason I'm saying this is because the only reason I'm still able to give this talk today is because of the teamwork. And all four of us actually worked together on this talk. And let me tell you why. So when we arrived in Columbia, of course, Anna Maria says, it would be a crime not going to Cartagena. This is a beautiful port city. So we went there. You can see we took a photo. We are all smiling. If you want to see how happy we are, I'll zoom into the face. We're all smiling really broadly. And notice, I usually don't call attention to my own face, but you notice my face, I'm wearing a different kind of pair of glass, right? You know, very nice, prescription made, you know, very beautiful. And on that day, Anna Maria said, what's the point of coming to Cartagena if you don't dip into the wave? So we start to test out the waves near our hotel. And this is on day one, on Saturday. Professor Cornell is an infinitely wise person. He has two pairs of glasses. One is for what he's wearing, and he's wearing still. The other one is a sunglass, which you can tell, maybe it's this one. And so he was wearing that, and he was said, okay, I'm just going to play with the wave with the glass. And the first dive, or maybe second dive, he went into this wave, the glass disappeared. Went into the wave. But Professor Thompson, that's why I'm saying it's a real collaboration. Professor Thompson was able to search the ocean and found the pair of glass. This is amazing. This is a true story. It's not made up. It happened just 2 days ago. And so he found this pair of glass. And we are all very happy when we have really nice dinner. And the next day we said, It's so amazing. You know, in Colorado, we never get to enjoy this warm ocean. Let's go swimming again. And being a little cocky myself, I was wearing this beautiful pair of glasses and I jumped into the ocean. And next time I know, that pair of glasses is gone. And I was really, because if I don't have that pair of glasses, I was almost like blind. I can still see the ocean. I can still see where Anna Maria is. Anna Maria, help me out. I lost my pair of glasses. It's not to be found. So Eric and James helped me searched for quite a while. We couldn't find it. And then it occurred to Eric, I got a second pair of glasses. I can lend this pair to Jun. And it's just by amazing coincidence, his prescription must be very close to mine, because as soon as I wear it, I can feel like I can see everything except it's very dark and I look cool. And I can feel like I can start to dance. So that's the reason why when we went to the clock tower, we have to go to the clock tower. I'm going to tell you a story about making a clock, so I have to go to there. You can see the time is exactly 4 o'clock, 4 p.m. when we took this photo. I'm wearing Eric's glass. Okay, at 4 p.m. Then I'm going to put this glass back on, because then Eric called his friends. Well, not even friends. He just called around in Cartagena. Was like, hey, can you help this poor guy who lost his glass in the ocean? You know, is it possible? Here's the I gave her the prescription, and she said, here's a prescription. Can you find him a pair of glasses that can actually work? So look, at the clock tower is 4 p.m. By 6 p.m., somebody called saying, look, I found a pair for you. So Anna Maria and I walked from the clock tower to somewhere, I don't know where, but it's like a 15 minutes walk. And I got this pair of glasses. And that's why I can deliver this lecture. You know, see, all 4 of us work together to get this working. You know, it's a teamwork. And so you can clearly see this is the important. You know, this is the, even in this kind of application, when we're having a lot of fun, you need to work together. So now let me tell you a little bit of a different time scale. Okay, that was one kind of time scale. The clock we make is no longer a mechanical clock. It's a so-called quantum mechanical system. And this, I'm using this little cheesy animation to show you electrons in superposition of 2 quantum states. And when you're in superposition of 2 quantum states, it's no longer stationary, right? Each state is a stationary state of the Hamiltonian. You put it in superposition, it's oscillating. And if you slow down that oscillation by 15 orders of magnitude, this would be like a pendulum, oscillates once per second. So it's a quantum pendulum. That's just for the easiness of the eye. Otherwise, you would never be able to see any of the motion. And it's kind of interesting. You can see this is a very macroscopic time scale. On the opposite end, macroscopic time scale, let's talk about the life of the universe. If you counted that in seconds, it's 10 to the 18 seconds. So you can see that making a clock, and now we are trying to reach on both ends, extremely microscopic small scale to extremely large scale. And this is something you will learn in physics. There's huge dynamic range. You go from very, very tiny things to very, very big things, and often they are connected. So it's interesting I'm making this example is, if anybody who does very little mathematics will say, oh, yeah, the geometrical mean of a 10 to the minus 15 second, we call it femtosecond, and 10 to the 18 seconds, if you put them together, it's a minute. And it turns out, okay, this is cutting off a little bit. Anna Maria Ray and I just published a paper this year, showed, for a particular atom called a strontium atom, we can put a system in quantum superpositions, and this superposition will live for 2 minutes. Isn't that amazing? That I see one student is like doing this already. So it's like, on one hand, you can visualize, okay, I have this microscopic pendulum that's oscillating once every 10 to the minus 15 seconds, and it can oscillate for basically 10 to the 17 times. How many would that be? If you got to go to your grandfather's room and he's got a pendulum and it's oscillating, imagine that's been oscillating since the beginning of the universe. That's how long that it is. That's what the geometrical mean of that means. So you like this kind of a clock to be the one that actually tells you the time, right? This is called a quantum coherence, good quality factor. That makes sense? So in some sense, since I started the talk, Eric might actually emphasize this much more. He has this very nice picture of a three-legged stool that modern physics is sitting on. And telescope and a microscope, I can argue, making a clock, it really is building a telescope because you can use clocks to detect gravitational waves. If you have enough sensitivity of 10 to minus 21, 10 to minus 22 capability to measure the time, when the gravitational wave comes, when the two black holes collide to each other, you will be able to see the time ripple. Or perhaps use this to constrain, we know that we have dark matters because there's stars moving at the edge of the galaxy that's moving way too fast than Newton's law would have told you. And there must be some chunk of mass in the middle. Is it possible to see this very feeble connection between dark matter and ordinary matter on Earth? And the only way to really find out is to build some of the most sensitive modern physics instruments to try to see that. And for that, we have been some grand visions, building these clocks in space where you can connect them all up. This can turn into a quantum network. Information can be transmitted back and forth, and time can be kept at 1,000 times more precise than the current GPS system. And what if GPS is really good enough for us to navigate? And the problem right now is that traffic jam is not caused by GPS, but mostly you can know where you want to go. But what if our civilization is going to go beyond Earth? Suppose we're going to live on Mars and so on. Maybe you want to build a GPS for the whole solar system. And maybe you needed a clock like this to be able to allow you to navigate in the universe. And a microscopic aspect of clocks would be, okay, well, we can actually use a clock because a clock and space is connected by Einstein's general relativity. So by measuring the time, you can actually know your local gravitational potential. So you can use this to start to find out the geodesy of your Earth and doing geology in a new way by building a clock network and finding out which area is more active, which area has lack of mass, and so on. So with that in mind, now let's get into the sort of the simple basics of quantum physics. We all know, so there's James Thomson has a very, very similar take on this. Everybody has heard of Niels Bohr, and everybody has heard Werner Heisenberg. Niels Bohr is one of the very early pioneers of quantum mechanics. In fact, when he put together a Bohr's model to describe atomic physics, that Bohr's model is no longer really accurate from the modern physics perspective, but the picture of stationary orbits is certainly survived the test of the time. And so the reason why we can build atomic clocks is exactly because of these orbits, electron orbits around the nucleus, and they are very well described by quantum mechanics. In fact, every atom, in principle, if you measure it well, the energy level between the energy between the two energy levels is a constant of nature. So you just have to do the measurements really well. On the other hand, there is a famous uncertainty principle by Heisenberg. And this comes from the fact that when I mentioned earlier, when you have two clock states, let's call it one is a ground state, the other one is excited state. There's nothing but two levels in your atom. And you put the system into a coherent superposition, like that, E plus G. If you have taken quantum mechanics, if you have not, maybe this is a little bit above you, but hopefully most of you have taken quantum physics. And this is the principle of superposition. Two states can exist simultaneously. But because the energy state E has a little bit more energy than ground state, you can see there's a little extra phase factor that's evolving in front of the energy state E. This is the energy difference between the two levels times time t. So if you can measure this little phase really, really well, after many oscillations, you can measure this energy. Or you can, if you know the energy, you can measure the time. So the uncertainty principle comes to the fact that you put the system in superposition. And then when you say, now after a certain time of evolution, I'm going to ask the atom, which state are you in? And the quantum mechanics tells you cannot ask that question. When you make a measurement, there's a true uncertainty principle comes in. You just don't know a priori whether the state is going to turn up into E or G. And so we can oftentimes, you can also use angular momentum non-commuting relationship of Jx, Jy equals to Ijz, that kind of relationship to derive this uncertainty principle. This is telling you that this is the fundamental uncertainty principle just because you're in the final action of flipping the coin, you don't know whether it's going to be head or tail after this evolution. So how do we beat, this uncertainty principle is really at the heart of the modern quantum physics. And I would argue whether you're building quantum computer or building clocks and so on, you're all working with this little noise and try to make them correlated or try to beat that noise. So how do we measure the system? We use lasers to do it. This is the evolution of the quantum system. And if we have a very coherent, phase-coherent laser, you can actually start the atomic evolution with laser and then watch the atom moves around in this equatorial plane of the superposition system. And afterwards, after a certain period of time, you measure it again to see whether it's in the ground state or excited state with this uncertainty principle, giving you the noise of your clock measurements. So the goal is to be able to have a very stable laser to be able to measure the evolution of the quantum coherence is to build this kind of another cheesy animation I have. Imagine the quantum superposition is oscillating back and forth, and almost like a two ball left and right is oscillating extremely fast. If you want to see where you are, you have to shine a laser that's almost exactly on the resonance of this atom. This is represented by the white sinusoidal wave. And I can see I put a white sinusoidal wave almost in phase with the quantum oscillation. And only by doing this, you'll be able to follow this oscillation 10 to 17 times and still be able to tell, roughly speaking, except the quantum uncertainty principle, where you are on the equatorial plane. And so the goal is to build modern tools like this incredibly good phase-coherent laser. Remember, the task is tremendously challenging. We're talking about keeping optical coherence for several minutes. Well, how do you do that? If you look at the electromagnetic spectrum, and modern life really relies on the control of radio waves, microwaves, infrared, all the way to the visible part, and ultraviolet, and so on. The laser that I use to talk to strontium atoms sits in this visible part of the spectrum at around 700 nanometer. And if you zoom in, it's a laser like this. It's called a laser semiconductor diode laser. Some of you may still use this to listen to CDs and watch DVD, watch movie. And so this laser emits a laser line width on the order of several hundreds of megahertz. So it's roughly speaking about 1 million times narrower than the entire visible spectrum. That's clearly too broad because remember I'm talking about 10 to the 17 kind of resolution. So then we need to go back to pioneers. I think Alejandra mentioned Jan Hall. This is the picture of Jan Hall. And in the 80s, he came up with these refined, I would say, the experimental techniques where he can use this very low, ultra low expansion piece of glass, drill a hole in the middle, and then attach 2 mirrors to it, make a Fabry-Pro cavity, and ask laser photons to bounce back and forth between the 2 mirrors. This is the front mirror, there's a back mirror somewhere there. And using systems like this, he was able to really push the boundary of stable lasers down to about 1 kilohertz or so. So from hundreds of megahertz down to a fraction of kilohertz, we're talking about another 1 million times zooming in. And I want to make a point, this technology that Jan Hall developed called a Peng-driven Hall locking, Hall is his name, is where made the LIGO to be possible, all the laser locking technique. And this is actually, never underestimate the power of this little laser locking. It turns out many, many loops, many, many modern AM environments require these kind of servo systems. This is still not quite enough. And it take another 20 years to develop yet another factor of 1 million. Now we have stable lasers supported by a piece of crystal, silicon. And we can, again, just following the idea from Jan, you can drill a hole through the crystal and attach two mirrors polished out of the same crystal, reattach it, so-called optical contact, and you're forming this incredible interferometer. And you can stabilize lasers onto this interferometer, and you can achieve laser line width on the order of just a few millihertz. Okay, now millihertz, 10 to minus 3 hertz out of 10 to the 14, 10 to the 15 hertz. That's 10 to minus 17. This is what I'm talking about. This oscillation can go 10 to the 17s, or the sinusoidal wave peaks and troughs can go 10 to the 17 times before you lose control. And so this is if you're interested, I'm actually very open. Alejandra can tell me what technical talk you want me to give, but I'll be happy to tell you about how to actually stabilize, how to build a cavity like this if you are interested tomorrow on the technical talk. I can also talk about something else. Maybe after this lecture if students can tell me what you want to hear tomorrow as a technical talk. But I propose that this could be one possibility. And to some of you may like to think in spatial domain, right? So I talked about time domain. In spatial domain, all you need to do is to multiply speed of light with the coherence time. So you know that the distance between moon and Earth is about a second for the light to go. Between Earth and the sun is about 8 minutes. So when I say, oh, I have a laser that can be coherent for 2 minutes, what does that mean? It means the light can go back and forth between Earth and the moon, 120 round trips, and we'll come back and still see a little fringe, like a microsecond interferometer. Okay, the Earth has a lot of atmosphere. It's probably not doable, but this is just to talk about in the vacuum, you should be able to do that. And if you start to develop lasers which will have coherence of 8 minutes, this is something we actually pursuing right now. We will be able to make a claim, our optical coherence length will be basically 1 astronomical unit. That's the distance between and the sun. So tools like this will become a very useful tool, a ruler, if you may say, for the universe, because you can now have satellites launched in space. This is a picture of so-called laser interferometer in space for gravitational waves, the concept proposed by former Jella colleagues who have since passed away. 5 million kilometers of those 3 satellites, and now with lasers like ours, you should be able to put it on one laser on here, and you can go back and forth between those satellites, and it will be completely coherent communication. You will never lose a wave in between those satellites. So another way of saying, you can measure 5 million kilometers with a precision of a nanometer or smaller. So with that, I want to switch onto atoms a little bit. I've been telling you how to use lasers to kind of probe atomic evolution and so on. Now let's talk about atom a little bit. And especially in the modern sort of a quantum physics, how do we go from one to many is a topic, because that's where you want to build a quantum machine that will function, that will deliver a useful function for quantum computing tasks and so on. So for that to work, you have to interconnect many quantum particles together. Clock is just one example of those. But for that, it's actually very good to go back to the beginning. Dave Wineland, of course, is not a very, very beginning. We are all always standing on the shoulders of giants. No matter how giant you are, you're still standing on the shoulder. This is the whole point of genealogy, like you were talking about. So Dave Wineland, of course, learned trapped ion from Hans Demmelt and Ramsey and so on about spectroscopy. But he in the 90s, he certainly absolutely was our hero, because he was able to use a single trapped mercury ion to define time, just one atom, okay, one atom trapped in the middle of this trapped ion system, and yet he was able to measure time better than the standards of time at the by cesium clock. So that was amazing. Well, at the same time, there's this vibrant field of laser cooling and trapping going on in the 1980s and the 90s. And the idea being, just in the vacuum chamber, you got a lot of hot atoms. And if you tune the laser just right to the right frequency from 3 different orthogonal directions, you can ask each atom to absorb many photons to oppose their motion. And very quickly, over a time scale of just a few milliseconds, my laser pointer color is very beautiful, just like the strontium cooling. You can, in milliseconds also, you can cool the atoms from thousands of Kelvin down to a fraction of a millikelvin. These days, we can go to microkelvin and so on. This is an amazing refrigeration technology. And this gives rise to, are you ready? Bose-Einstein condensation. That's what Eric's topic is going to be. Well, Eric is actually not going to talk about that. He's going to talk about EDM. But this is what Eric, Wolfgang Ketterle, and Carl Weinman was able to use this technology and then put a little bit more, like evaporative cooling and so on. So they were able to cool bosons. Bosons are very social particles. They like each other. They like to bond together. So when you cool them down, they eventually get into a phase transition where all boson particles would just collapse to the ground state. And this is so-called, it's a new state of matter called Bose-Einstein condensate. Another Jilla colleague, Deborah Jing, who actually was Eric Cornell's postdoc. Unfortunately, she passed away, but she is a very close colleague of Me and Maria Ray and Eric and James. She was the one who actually created this very low degeneracy, very low entropy system called a degenerate Fermi gas. And the fermions don't like each other. You have heard the Pauli exclusion principle? Yes, that's responsible for periodic table. Two fermions don't want to be in the same place at the same time. Bosons love to be on the same place at the same time. Fermions are like you're only occupying one chair at a time. You don't jump onto your neighbor's chair. And but when the temperature is sufficiently low, each fermion has its own orbit, and there's no holes in the middle. And that becomes really orderly. If you calculate the entropy per particle, it's very low. And so she was able to prepare a system on the Earth where you can have a degenerate Fermi gas, meaning you can have particles one by one lined up from the very bottom of the trap. Every single energy level is occupied by one and only one particle, all the way up to the so-called Fermi surface. So it's kind of interesting that my career, I came back to JELA in late 1999, and I was thinking about frequency combs, as Leandra said, but at the same time was also thinking about how to build a clock that can be as good, but of course, as a young professor, you'd always think, how can I do better? And the only way to do better than Dave would be to many of them. And so if you think about, well, Eric and Debbie had already prepared extremely low entropy system. Well, maybe there's a hope if you have an optical lattice, which is basically interference of lattice of optical beams, forming these interference patterns at nodes, antinodes, and atoms can be polarized, so they can trap these atoms, one and only one per interference antinode. If that's the case, then potentially you could be doing this kind of a clockwork, but it was many, many more particles. And then remember, each particle, each atom in superposition has a quantum uncertainty principle. So in order to beat that uncertainty principle is to measure many, many times. Okay, so that makes sense, right? This is trying to take advantage of all this modern AMO physics development to build the next generation of clocks. There's one more catch we have to solve. For ion, Dave Wine, because the charge is separated from internal energy level structure. So you can use Coulomb charge, you can use Lorentz force to confine ions, entrapped ion. For neutral atoms, you don't have ion, it's not charged. So in order to trap them into this crystal, you actually have to turn on the laser, it's called optical tweezer. The laser can polarize the atom such that certain energy levels will be bend down, meaning at a high intensity level, the energy level gets pushed down. So the atoms will actually be confined here in the maximum intensity. Certain energy states will be pushed up. And so in general, this is if you pick a pair of energy state in an atom, and you shine on a wavelength of a laser, this is typically what will happen. And in fact, there are many different kind of forms and shapes will come. But the problem with this for clock is that the laser has an intensity. The whole reason that you're making a trap is because intensity has inhomogeneity. It's a spatial dependent intensity. That's why our atom can go to this intensity maximum. And what that means, if you have these energy scale that's ground state, excited state have a different so-called AC stock shift, light shift. Well, the atoms have a different sort of a position with respect to this trapping potential. And you can visualize this as if different atoms now have their energy levels being pulled apart in a very different way, because each one of them, the separation is depending on the local intensity. And so if you use that to build a clock, that would be a problem, right? And fortunately, there's this so-called magic light trapping idea came around where, well, the states of the atom is multi-leveled. And so maybe you can find always this particular wavelength that's so special that for this pair of the ground and excited state for atomic clock, you can find a particular wavelength where the AC stock shift or the light shift of the two levels are matched. So you can think of now if this represents two orbitals of ground and excited state, I know I'm using a little kind of an animation kind of a way to tell you the conceptual drawing, but at least you can see the all orbitals now look identical again, just for that pair of pair of energy levels. They are still deformed with respect to other energy states. But since the energy between the two states here of the so-called clock states is what I cared about to make it correct, then I just cared about finding this wavelength where the differential shift disappears. And this is called holding atoms in magic light balls. This is actually Professor Hidetoshi Katori from University of Tokyo around the time of 2000, when I was actually still a postdoc with Jeff Kimball, independently came up with these kind of ideas. So with that all in place, now we can actually do a clock. We have a laser, we have atoms confined in the trap. The trap can be made where the ground state and excited state have exactly the same trapping shifts. So you can now form a very simple interference pattern with just a simple laser beam, like the one I'm holding in my hand, this laser pointer. If I put this against this white surface, if this white surface is a mirror reflecting back, in between there's a lot of pancakes being made, because that's a standing wave. And anybody who has learned about waves, sound wave, and so on, can make those standing waves. And what I'm showing you is basically pockets of standing waves. And at the antinode, where the atom can be trapped, they can be attracted to the light. And we usually trap dozens or hundreds of atoms per pancake there. And we pick the fermions. Remember, fermions don't like to hit on top of each other. And as soon as in clocks, the last thing we want is to have a very precise clock and let them hit on each other. So we use fermions to do that. And what's interesting is, so then we put a laser on and you start to rotate on this block sphere that I was showing you, this picture of the block sphere where you have a ground state pointing down, excited state pointing up. Now I'm fulfilling my dream. I can have many atoms trapped in these arrays of these pancakes, and each one of them represents a little clock handle, but I can measure many thousands or hundreds of thousands of them. And the precision went ahead really nicely. It very quickly we surpassed the cesium fountain clocks and so on in 2008. But as it progressed, soon we hit a problem, and that was it was actually an interesting year. 2008 is when strontium atom surpassed the performance of a cesium clock. 2008 was also the year we hired Anna Maria Ray into Chile. And 2009, we saw problems. The problem turns out to be the following. These atoms, these are fermions. And the fermions just means that they cannot sit on top of each other, but nothing prevents them from circling around each other. They can actually do this kind of a motion. When you describe the circular motion between two particles, it can be anti-symmetrized. And this is what fermions like to be. They are total wave function. The ground state, for example, is symmetrized ground state plus excited, ground excited plus excited ground to describe the pair of atoms in the internal degrees of freedom. The external degrees of freedom, this N1, N2 represents the trajectory in these pancakes. This has to be anti-symmetrized. And you can visualize this as if the two particles are just moving around each other, circling around each other. And when the precision goes well enough, even this persistent interaction, which we call a P-wave interaction, gives rise to frequency shift. So any pairs of atoms start to interact, and in fact, this can even become collective, all the atoms interacting with each other. And we can actually measure clock frequency shift at a few parts 10 to the minus 17. And this turned into a really important problem as a systematic, because it feels like that's a barrier in the road. We want to have lots of atoms to do better than single trapped ion clock. But on the other hand, there's a lot of interactions. And this interaction turns out to be actually interesting because you can study spin models and so on. And so we teamed up with, this is exactly where Anna Maria, 2009, I think the very first paper you published was addressing this problem. Like, it was really amazing. The very first paper, she said, oh, I figured out the way why your clock has a shift. And then this has really gone on to many, many amazing spin model to this day. And this is Anna Maria's one of the key weapons she uses to solve a lot of problems. Another gentleman here, he's a Professor Peter Zoller, who's in quantum information and puts in the kind of a quantum information language. And it's a very, very beautifully connecting metrology and information science. So you can see this is a collaboration where I had made a huge difference. Now I can tell you one story of how we solved that problem. Okay, so after Anna Maria Ray pointed out there's a problem, so how do we solve problem? Well, there's many different solutions. Here's one of them, very practical solution. We just turn the lattice to be extremely shallow. Okay, this very shallow lattice, meaning only just a few photon recoil. I don't know if that's a good intuitive unit. If it's not to you, I apologize. It's very low, basically you have barely enough laser intensity, barely enough tweezers to hold the atom against gravity. Otherwise, if you let it go, the atom is going to fall down, okay? So we just barely hold it. And the force is so weak that you can see this lattice, this periodic potential gets tilted by the gravity. This is something we all learned in high school. If you lift atom up by lambda, the energy you gain, the so-called gravitational potential energy, has nothing to do with general relativity. It goes up by mgh, right? H being the distance. So in a system like this, and what turns out what's really interesting is that the trapping potential is so weak that you can no longer think of the atom as individual particles. Rather, you should think of this as a superposition of waves that's actually occupying different parts of these trapping potentials. So instead of thinking of each particle as localized here, you can think of this particle's wave function actually spreads out to its neighboring pancakes. And the consequence of this is that when I drive the transition from ground state to the excited state, remember this is a magic wavelength, so the potential looks very much the same. When I drive this, the atoms which are in the same pancake, they still look like identical fermions, so they can only do the motion of a circular motion with respect to each other, and that's a p-wave interaction. However, since the wave function of this particle extends over there, and this particle's wave function extends down here, and so on, these particles do not have to be necessary to be indistinguishable fermions. They can be distinguishable because the laser wavelengths that's exciting these particles can be incommensurate with the distance between pancakes. In other words, different locations of atoms picks up different phase shift of the laser. So they become distinguishable, just like these pictures are showing. When these are distinguishable particles, they are like classical physics. They can collide S-wave, P-waves. S-wave just means they do not have to have angular momentum between them anymore. They can just head-on collision. So you can have particles can come together, interact with each other in a straightforward manner, versus the particles who interact with each other kind of in a dance, circling around. Yeah, question?
Simulates the potential barriers faced by the free electrons.
By free electrons. So you're talking about tunneling, or you're talking about, I mean, there is aspect of the wave function that's permeating beyond the barrier, if that's what you're looking for. Yes, yeah, very much so. So, if you raise the potential deeper and deeper, you can see this part of the wave function cuts down. So yeah, yes, in some sense, that's exactly right. You have to have certain parts of wave function going underneath the barrier. And tunneling is another way of thinking about, and here I'm trying to describe the kind of a stationary quantum state. Yeah, but if you cut yourself off, like if you say, I'm going to force my atom start here and let it go, it will actually go through some oscillation called a block oscillation. Yeah, yes. Those states these potential were created by laser. Yes, that's exactly right. And the lasers are polarizing these atoms, attracting them or repelling them. In this case, we attract them. Okay. Makes sense? Yeah. Yeah, thank you. Thank you for any other questions, please don't hesitate in the middle. So what I'm trying to say is now you got this two different kind of interactions going on. One is identical fermions interacting in each pancake. The other one is between neighboring pancakes, the atoms can interact through S-wave. So the interaction strengths can be adjusted just by either, you can pull the pancakes out, just by adjusting laser, the angle of how they interfere, or just by adjusting the depth of your light intensity. And you do this to a point where you can balance it. So we actually have those tricks where we have this microscope that's very high resolution, and you can actually see this is a real atomic picture. of the atoms confined in these 1 millimeter long sort of a crowd. These are individual atoms there. And each one of them, we can measure their clock frequency shift. This is actually very powerful. You got a microscopy and a spectroscopy all combined in here. So you can see this is plotted as a clock fractional frequency shift. And you can see the frequency shift normally follows the density profile. The middle part is very dense. The frequency shift is very large, and then go on. And so, but by tuning this to a specific depth, balancing S wave, P wave, you can see actually, on this picture, looks like the frequency shift is totally flat, regardless how many atoms you have, whether it's here or there, the frequency shift is all the same. And this is just one simple trick that Anna Maria Rey's group figured it out and told us, oh, you can do S wave, P wave balancing, and we can immediately benefit this in the experiment. So with this, we went on to do this experiment called the gravitational redshift. Now, this is no longer gravitational energy that I'm talking about, although we can actually measure gravitational energy just by measuring energy difference between this pancake versus that pancake. You can actually pull out this gravity. So this allows you to measure gravity. But this picture is actually measuring real general relativity effect, which is the so-called gravitational time dilation. If you have Earth here and the space-time is curved, and so the atom, which is sitting away from the Earth a little bit more than the atom sitting closer to the Earth, their time will speed up. And so you can look at the top half of the crowd versus the bottom half of the crowd and actually compare their time. And you can see that you can average down all the way below 10 to minus 20. 10 to minus 20 represents a frequency shift of a clock. If you move your watch, if you take down your watch, move it by 1 human hair width, and the time slows down or speeds up by a fraction of 10 to minus 20. And now we can see those things. And so this is amazing in some ways, being able to be so sensitive to gravitational potential energy difference in space. But just imagine if we keep going. For example, this year we already moved a little bit better, but if we imagine you keep going to a point where you can actually resolve gravitational redshift on the length scale of every optical wavelength, or on the scale of the quantum mechanical wave function. So imagine every pancake, the time is evolving differently. Now, here when I was describing to you, S wave, P wave comes from the fact this wavelength of a clock laser is different from the spacing of the lattice. But even if the spacing of the lattice is the same as the clock laser, just the mere fact that the gravitational potential energy will cause different phase shifts among these different pancakes, you will turn these identical fermions into non-identical fermions just by gravity. So this is not quantum gravity, but this is where gravitational physics start to have real impact on quantum mechanics in a dynamic, in sort of a measurable dynamics that you will see in a microscopic evolution of quantum system. We are not there yet. In order to do that, will require us to make the clock 100 times better, because we can only resolve 100 micron. We would love to go down to being able to resolve 1 micron. Then there will be sort of a new, very new, interesting physics to come out, and this is actually some of which is already being summarized in this theory paper with Anna Maria Rey's group. Is time up, or? Still has some time, yes. Okay. If we don't finish today, we can also take some time for. Yeah. So okay, so these are not going to be easy. To make a clock another 100 times better, that's not easy. Now we already pushed really, really hard. And how do you continue to advance the field? Well, one possibility, I know James is going to talk a lot about this, the so-called beyond the standard quantum noise, beyond the standard quantum limit. So as I showed this picture earlier, you put a system in coherent superposition, you can probe with a coherent laser, and the one way to do it is to average the noise away, is just to make many copies of this. Essentially it looks like, oh, I'm making a many different pendulum, and if I average all of these pendulums, the noise will go down as 1 over square root of the number of pendulums you have. This is what typically comes out when you have a white noise. The more average you have, the more noise will go down in a square root fashion. But what if you start to involve modern concept of so-called entanglement? And you can see what I did, again, very cheesy animation. This little ball that's supposed to be spheres look like standard quantum noise. And now if imagine all these 5 independent atoms suddenly have the strong quantum correlation where their quantum noise become correlated. Or another way of saying, if I measure noise of this particular pendulum, I already know the noise of the other ones. Okay, if you can do that, then you have a 5 pendulum, you have only 1 copy of noise, you still have a 5 copy of signal. And that will give you a signal to noise ratio of 1/n. So this is where the entanglement becomes very powerful, but also, you know it's not easy because these particles want to have independent noise. That's what the quantum mechanics likes to have. They like to have individual particles like to have independent noise. If you force them to be correlated, they're very easy to be decorrelated or decoherent and so on. So you can see why so many people are working on this, because the gain can be amazing. If this n is 1,000,000, you go from 1/√n to 1/n, you gain by a factor of 1,000 right there. Okay. These are some of the students who are working on this experiment. So, so how do we do that? You know, so you are getting familiar with the picture of the quantum noise on this equatorial plane. Well, you're thinking about, what if I can make the noise shrinking down to this look like a Cuban cigar? In Cartagena, we were pulled into a store. They said, do you want a Cuban cigar? And that, it looks just like that. And you can see this is much better in terms of measuring noise of where you are on the equatorial plane. And okay, well, that looks like a good idea. How do we do that? Fortunately, there are pioneers who have been doing this. And one of them is sitting in this room, James Thompson. And it's, again, a really interesting kind of a lineage. Vladan Vuletic is Ted Hinch student, Steve Chu postdoc, and you can see all these connections. And James was a postdoc with Vladan. And so the idea of being able to put atoms in between pair of very highly refractive mirrors, you can then turn this system into almost like a little spy. So imagine that you put atoms in a coherent superposition between ground state and excited state. Okay, so we said this is a very sacred superposition. You're not supposed to make measurements. As soon as you measurements, you could destroy the coherence and so on. But turns out, if you got plenty of atoms in here, and these mirrors are extremely reflective. You put 1 photon inside, this photon is going to bounce back and forth many thousands of, hundreds of thousands of times. And as the photon does this, it does not remember which atom it has interacted. So all these atoms, thousands of them inside the cavity, is interacting with the same photon many times. And it turns out that's a way to kind of spy on whether collectively these atoms are in ground state or excited state. And you can do that without destroying the coherence, which is a really important so-called cavity QED-based so-called quantum non-demolition. And I'm relying on James. Later in the week, he's going to get into more details of this. And this turns out to be an incredibly powerful technique. So visually, you can think of, you have a block sphere distribution of the quantum noise. You do this little spy thing with a cavity, the noise gets pushed down because you know whether the atom's actually in the ground state and excited state without destroying the coherence. Sounds magical. It only works if you have lots of atoms in here. And then all you need to do is rotate this by 90 degrees like that, and then start to evolve under the clock, and you should be able to measure clocks much better. When I say much better, I should be humble to say this because we only gain a factor of 3 dB or so. But we made 2 different samples. We put a sample A in here, and then move out, and put a sample B in there, and move them out. And we can compare 2 spin squeeze samples and directly verify that indeed the clock performance is actually better than the so-called standard quantum limit. And it's now getting down to the state-of-the-art 10⁻18 level. So this is one way to move forward, is using entanglement. The other way to move forward is actually just get lots of atoms, right? We talked about 1/√n. So if you have many atoms, this will be helpful. So we have been thinking about the three-dimensional system. If you put 1 million atoms in there with a coherence time at, as I mentioned earlier, 2 minutes, you can build a clock at a 10 to the minus 20 at a second, and this will take you only 10 to the 4 seconds to go down to 10 minus 22, which will allow you to see 1 micron gravitational redshifts. So that's another way to do scaling up the atom number. It's a plenty of good quantum system. It just doesn't use quantum entanglement. But it turns out there's also plenty of opportunities. Here's where we also collaborate very strongly with Anna Maria Ray's group, because when you pack so many atoms together and you have a little light to come in to propagate, well, all these little antennas gets turned up. Each atom turns into a little antenna, and this next antenna is going to interfere, just like your cell phone tower. If you have to build too many cell phone towers, your cell phone probably doesn't work well. And all these antennas interacting with each other. And it's actually an amazing opportunity to study this collective physics of how each antenna is moving around, is interacting with the next antenna and so on in a collective fashion. But also this turns into a really important problem, because if the antennas interacting with each other, it will cause frequency shift. And we have to understand this before we say we can make a clock that's accurate. So there are a lot of those. I think in my remaining maybe 10 minutes or 15 minutes, I will tell you a little bit about, and keep going on this number scaling game. So, you know, in some sense, the historical lesson that atomic physics we learned is actually in the 1950s and 60s of nuclear physics, where we were taught mass power spectroscopy, when you have very highly charged nucleus, ion nucleus, sitting in the middle of a crystal, and when gamma ray gets absorbed, you can actually see spectroscopy without recoil, even though gamma ray has a huge photon momentum. That's because the whole recoil is being absorbed by the entire crystal. That's called a mass spectroscopy, right? And you can see the atomic clock, whether it's trapped ion clock or neutral atom clocks, they bear resemblance because our atomic clock is all recoil-less. When the photon hits on these atoms, the recoil is taken up by this ion trap or by this lattice system. And no atoms individually experience photon recoils. The difference is, of course, we do this coherently. Mass Bauer was incoherent. But if you can turn this into a coherent spectroscopy, then perhaps, you know, in a crystal, you can have 10 to the 22 number of nuclei working for you. And that square root of 10 to the 22 of 10 to the 11. That would be an incredible dream coming true. You don't need an entanglement. It will get you going on clocks to the 10 to the minus 30, given the time. So that's one motivation, I think, that we're starting to think about. Well, maybe we should look into the nuclear physics, possible to do nuclear physics. The difference between nuclear physics and atomic physics is, of course, in atomic states, we're looking at the energy level structure of electrons moving around the nucleus. And typically, energy scale is accessible with a visible light, with the energy scale of about EV scale. The wavelength is typically on the order of 10 to the 3 nanometers, 1 micron or so. And that's where we talked about building lasers. But in nuclear transitions, of course, energy scale you typically hear from nuclear physicists will be mega EV, kilo EV, and so on. And you don't really have lasers that can go to this kind of energy scale. And so if you want to do nuclear physics, you go to user facilities where you have X gamma ray photons coming out of the synchrotron radiations. And so that has been sort of the story where the nuclear physics typically use incoherent light source to do nuclear energy probing. But there's one particular species called a thorium-229 that actually has an energy state that's about 10 eV above the ground state and has a long enough lifetime, making it very interesting. It's got a 10 eV, meaning 150 nanometer kind of a wavelength, ultraviolet, deep ultraviolet, vacuum ultraviolet. And lifetime is long enough, perhaps this is an interesting candidate for clock. And so you can see thorium-229 is actually very unique, sitting down here, occupying almost the atomic energy level structure. But nevertheless, it's a nuclear transition. The next one is actually uranium, and there's another one, scandium, and people now in Europe have used accelerator physics. This is 10 keV, they can actually excite the nuclear transitions also, but incoherent. this is a story that I want to tell you with a laser coherent excitation. This Ecke Pike at PTB in Germany has recently observed this transition by laser excitation and watching the fluorescence. His laser system is very broad, and you can see the line was on the order of tens of gigahertz, 20 gigahertz. And this work was very quickly followed by a group at UCLA, Eric Hudson, who actually was JELA-educated PhD. And his group very much was on the similar time period, performed very similar experiments. And so the question is, can we develop the similar kind of a storyline, the atomic physics I was telling you, very, very long coherence laser to excite these nuclear transition? So this is really the kind of the final story about the combination of light and matter coming together and do something interesting. So this is, again, the spectrum of the electromagnetic spectrum. This is the visible part. Now I'm emphasizing on going to the shorter wavelengths, the vacuum ultraviolet, extreme ultraviolet. There are a lot of interesting physics you can probe, but we just don't have much coherent laser light over there. So you have heard Alejandra say frequency comb. This is the idea that won Jan Hall and Ted Henschel Nobel Prize is if you can have a train of pulses, extremely well-controlled train of pulses with optical carriers underneath the envelope, you can translate this by Fourier transform into the frequency domain, looks like a comb of spectroscopy lines. And these lines across very broad optical spectrum, and it's very regularly spaced. Every frequency can be controlled. So this tool has essentially brought us the connection of, if you build one stable lasers in the visible part of a spectrum, you can cover anywhere you want it. Or if you have a visible laser, you can turn that information into the microwave or radio frequency through this kind of a gear-like mechanism. And so this is all very well known now at this point after 20-something years. But this part of the spectrum, vacuum ultraviolet and so on, is pretty much virgin land where we don't really have access to very coherent laser light to do this nuclear clock type of work. But some of you may have heard attosecond physics. The attosecond physics, these are three pioneers who recently won the Nobel Prize for driving attosecond physics forward. The idea basically being, if you give the atom sufficient laser power, it's so much electric field, it's going to distort Coulomb potential. The electron is going to tunnel out. The question earlier you asked, it becomes a free electron. But this free electron then will be driven back because the laser field reverses its direction very quickly. It goes back and bends, recombine, recollision with the nucleus. And in doing so, you seemingly extremely violent process, you can generate these very, very fast order time dynamics called attosecond physics. Basically, every time, this is optical frequency going up and down, oscillating at a femtosecond period. Every time you have a zero crossing, you can have this band. And so this time scale that's coming out is the odd harmonics of the fundamental light you're driving it. And the harmonic can go way, way out all the way to extreme ultraviolet. And each one of them has a bandwidth of the entire visible part of the spectrum. So this is a very interesting physics, but it's not a high-resolution spectroscopy tool either in terms of the frequency domain. What you need to do is, instead of just having one laser pulse, you need a very big, powerful laser pulse to be able to distort the Coulomb potential. But doing one time is not enough. What if you can do this over and over and over, every 10 nanoseconds you can do this? And when you do it, also it's in a phase coherent fashion. Then you can have actually interference between this pulse to the next pulse to the next pulse, such that each of these harmonics can be subdivided into a frequency comb. And this is called a vacuum ultralight frequency comb. So this is the combining attosecond physics, extreme nonlinear optics with the precision metrology. And you can see this really coming from very different aspects of laser physics, but they meet together and create a very unique tool. So now you can shift your laser wavelength to very, very blue or ultraviolet or deep ultraviolet. In fact, we created a frequency comb all the way down to 50 nanometer, 50 nanometer. And it still has these kind of a spectral resolving power. So with that, I just want to recognize this was actually Dr. Jason Jones when he was postdoc back in 2005 in Chile. He's now a professor at the University of Arizona. And together, we initially worked out these concepts and the technology. And it took 20 years to perfect the system. And finally, we can now, a crystal coming from Vienna, Thorsten Schum's group, we have these thorium-229 nuclears doped inside the calcium fluoride crystal. And you can throw these vacuum ultraviolet frequency comb on it. And the comb has a repeated frequency spectrum. And if you don't know where the laser is going to hit, you just scan the comb like this, very slow motion. Every line scans once over to the neighboring line, you cover the entire spectrum. And what we uncovered is not just one line, we see actually 5 of them. And it turns out the 5 has something to do with how the nuclear is deformed, and it forms a so-called a quadrupole moment. Remember, nuclear is charged, and this quadrupole moment can interact with electric field gradient inside the crystal to have a split of patterns like this. So by measuring these splitting patterns, we can immediately determine the nuclear quadrupole moment of the excited state, nuclear quadrupole moment of the ground state, and actually even measuring nuclear charge radius of the ground state and excited state. The nuclear properties cannot be measured precisely. Okay, it's just one nucleus. It's not a AMO physics where lasers can now deal with any atoms. It's a one nuclear physics, one nucleus, one nucleus species. But nevertheless, it's really exciting. Think about in the future, we can use coherent lasers to start to open up the landscape for precision measurements. So with that, I think I want to end here, telling you the story of atomic clocks and nuclear clocks cannot be connected. And after all, the mass power spectroscopy is where historically gave us the first measurement of the redshift. This is the building in Harvard where they were putting nuclear material emitter in the basement, let it gamma ray propagate into the ceiling, into the, I actually don't know the story. How many stories? 7 stories? Into the top of the building, let's say, and the absorber is sitting up there, and they, Pound Arabica made a claim. They saw the photon frequency shifted to the red. This is where the red shift came from. But of course, this is all based on your perspective, right? In our laboratory, we have observer here, which is looking at a coordinated system that's being distorted by the gravity of the Earth. And you can the clocks. If you were a little ant living on these atoms with these atoms on each pancakes, the time looked exactly the same. But you are sitting outside as an observer and looking at a coordinate system from bottom to the top, and the clock's actually running differently. So these are, of course, connected to the same physics. It's just frame transformation. But now with the nuclear clocks, of course, the goal is to be able to push the nuclear clock to the scale where you can actually see time scales which are distorted by gravitational potential. And I think this lies potentially amazing opportunities to even eventually probe quantum gravity. So with this, I want to thank you for your attention.
So if there are any questions, comments.
So you showed that ladder, pancakes, and then you said that you could take a photograph of that.
Yes.
And then from that photograph, basically create a plot.
Yeah, actually, let me go over there. The particular picture of what you were asking about.
I was wondering if you could elaborate more. How do you take that photograph?
So you're talking about this particular picture, right? Yeah. So this is just a high resolution imaging camera. And so what we do is we use lasers to prepare all the atoms in certain coherent superposition. And then we wait for a certain time. We put another laser pulse coming in to read how each atom has evolved in the Bloch sphere. And at that point, we can turn on a laser which will allow you to scatter lots of photons from these 2 clock states, connecting one of them to another state. that will allow you to scatter a lot of photons. And we just look at that, all these photons being collected into here. So the atoms sitting in one particular state will not scatter any photon. The atom sitting in another state will scatter all the photons. So we can take that image first, blow away all these atoms, and now we put it using clock to put another state into the state which we can see lots of photons, and we image again. Now, 2 images later, we pretty much know each atom is at what frequency. So it's like combining really like microscopy because you want to know the atomic distributions. We don't have the resolution to really see single atom. You can see it's blurred. But people these days have done spectroscopy, have done, if you make this into a 2D, if you put a camera right on top of it, if you have just a 2D plane, you can actually see individual atoms. It's called a quantum gas microscope. So we don't do individual, our resolution is a few micron. But we at least will be able to see the collection, like which part of the distribution has a much higher density versus the other. And you can see this density profile really mimics the frequency shift profile. And then this allows you to test this idea of balancing the interactions to remove that shift.
So I imagine that each of the pancakes you have a lattice.
Yes, each pancake is essentially a site to contain atoms, and they have different number of atoms contained in there.
What is the limitation on that size?
It's a limitation. Okay, what's the limitation on the size? What's the size of the beam spot? It's limited by the so-called Gaussian beam. So the laser coming out, lasers were very well guided, and so, but there's nevertheless the transverse mode profile, and that's confined by this. But remember, the transverse mode profile. I only have this pair of glass left, so I don't want to do experiment on it. But you can take it down and then shine through it, and you can see how the beam propagates. And so we can manipulate it. Yeah, we can make this profile bigger, smaller. In fact, we have been trying to make this bigger and bigger and bigger because the bigger effective density is smaller, but you need more power. So it's being an experimentalist, it's always confined by how much money you have, how much creativity you do, how many friends you have as a theorist. These are all the important ingredients.
Any other question or comment? Anyway,
You spoke about the resonance in the next slide.
Resonance. Okay. Here? Okay. Yeah. Cavity QED, quantum electrodynamics. Sorry, I didn't use I apologize for that. This is a really jargon. But what this is that you're using pair of cavities to confine an electromagnetic mode that's confined in here. And this mode will interact with atoms in here. And the cavity QED is just a traditional way of saying, I use the pair of mirrors to modify the structure of vacuum. That's what this is coming from. But in this particular case, you can think of this. Actually, I didn't say this aspect of the work. We can turn this lattice as if it's an elevator. We can move them up and down. And so we can prepare atoms in sample A. And in fact, they were all prepared down here. And we just move them up like elevator. And then they sit in